All right, so welcome back everybody for today's session of the Cardiff Analysis Seminar. So today will be the last session before Easter, so we'll now take a 3 weeks break and we will be back on the 19th of April. So until the 19th of April, we will have no more seminars. And today we're delighted to have Simon Larson from Caltech, who very kindly agreed to give a talk at such an early hour in the morning for him, so we are most grateful. And he will talk about the spectrum of the Kronig-Penney model in a constant electric field. So over to you, and thank you very much.
First off, thank you, Matteo, both for the introduction and the kind invitation to give a talk here. Although it is early in the morning, it's always nice to be invited. And I've never been to Cardiff, so even if it's only virtually, it's nice to be invited. So what I'm going to talk about today is some recent joint work with Rupert Frank on a particular family of one-dimensional Schrödinger operators. And well, I say recent, but it's not even on the archive yet, so it's brand new out of the box. But hopefully we should have something on the archive in the next few weeks, maybe a month if we're slow. Okay, so what is the problem that we're looking at here? It's the following family of one-dimensional Schrödinger operators. Just as usual, we have a second derivative, and then we have a potential that is split into two parts. First, we have a fairly nice part, which is just a linear function, which I will write as minus f times x. And then there's a periodic part, which is a sum of Dirac deltas on the integer lattice with a coupling constant lambda in front. Now, this is sort of formal with the Dirac deltas, but you can make sense of them in this one-dimensional setting. And you should really interpret that as the derivative of the functions in the domain of this operator having a jump at the integer points, which is proportional to the value of the function there, times this coupling constant lambda. Now, the question we sort of ask is, what is the spectrum of these operators? And in particular, how does it depend on f and lambda, these two parameters that we have? There are three sort of very basic cases which are fully understood. And that's when either f or lambda or both are 0. And in all three cases, we have purely absolutely continuous spectrum. The structure of that spectrum is rather different depending on the cases, but it's always absolutely continuous. So the first case is sort of the very basic case, the Laplace operator, when both f and lambda are 0. So we have spectrum covering the positive real axis. If instead f is non-zero, but lambda is, then again, we have only a C. This is the Stark operator, but now the spectrum is all of the real line. And in the third case, when f is 0 and lambda is non-zero, this is the Kronig-Penney model. And we have AC spectrum, but which now has a band gap structure. So we have bands of AC spectrum and gaps in between going off to plus infinity, but it's again bounded from below. So that's essentially the only case where we know exactly what happens. It was suggested by Au in sort of the 90s, or 1990, according to the paper, that the spectrum in general can be fairly exotic and in fact depend on number theoretic properties of the field strength F. This was also made somewhat more rigorous. Au was a physicist, I think. It's very heuristic, his argument, and I don't fully understand it, to be honest, but I think there's some truth to it. But this was put on sort of a more mathematical footing by Buslaev in 1999. And perhaps a bunch of papers around there. So what do we actually prove in this new paper? Just to sort of put ourselves in a definite setting, I'm going to assume that f is positive. F negative can be reduced to this case just by changing the orientation of the line. So this is not really an assumption. It's just for concreteness. And what we prove, hopefully, very hopefully in 2021, is that if we assume that our field strength is a rational multiple of pi squared, and lambda is arbitrary, real, then the absolute continuous spectrum of the corresponding operator covers all of the real line. So that's like in the Stark case. We have no singular continuous spectrum. We might have a bunch of eigenvalues, but we don't know precisely where these eigenvalues might be. They can only be placed on some subset of a lattice. And that lattice can be written explicitly if we write f as pi squared over 3 times q over p, where q and p are natural numbers, which we can due to the rationality assumption, then we might have pure point spectrum in this lattice here, where m ranges over the integers. And it might be worth noting that by translating this operator by 1 or by any integer length, it's unitarily equivalent to itself plus f, or plus an integer multiple of f. So the spectrum is f periodic. So in particular, we see that if for some m here, we have an eigenvalue or we don't have an eigenvalue, one of the two is true, then we again have the same situation at m plus q. So it's only really q congruency classes that we have to check here to fully determine the spectrum. But so far, we don't really know what happens at these points. I do know that there are situations where we don't have eigenvalues on some of them. I would be surprised if there are actually no eigenvalues. At the moment, at least, I think that most of these guys are eigenvalues. Okay, so a few remarks. This confirms in part the predictions of Au and Buslaev in sort of the rational case. This is what they expected there, as far as I can understand, at least. What happens in the irrational case is still very open, but I want to sort of emphasize that although this is the end sort of spectral theoretic result that we prove, most of our work goes into reducing the sort of proving spectral results for this model into proving corresponding results for a discrete system. And this reduction to the discrete system works for arbitrary field strength f. It's just fully understanding that discrete system we can't do unless we have the rationality assumption yet. I should also say that this periodic perturbation of the Dirac deltas here is in some sense critical. If you look at sort of the Stark operator perturbed by a periodic potential V, and this V is somewhat nicer than the Dirac deltas, for instance, L1 and H minus 1/2, then it's known that in general you have AC spectrum covering the real line. While if you go slightly worse regularity than the deltas, so delta prime is essentially where we end up then you have no AC spectrum. And this was proven by Perelman in 2003 and Avron-Exner-Last in 1994, respectively. So we're sort of on the very boundary of regularity here, even though the deltas are not regular at all. But it's sort of expected that something interesting might happen, which is what we believe is the case when we sort of go over to irrational frequencies. We might have pure point spectrum or singular continuous or more interesting things happen. Okay, so apart from this model here, we also study a related random model where we, instead of having all the coupling constants in front of this Dirac comb equal to the same number lambda, we look at a sort of almost periodic potential with random coupling constants, where these Gn depend now on which integer you're at, and their IID random variables with mean 0 and variance lambda squared. And I assume here that their common distribution is compactly supported and absolutely continuous. That can be relaxed substantially, but for the purposes of this talk, you can assume that they're very, very nice. Now, in this setting, what we prove is, well, first off, this defines a self-adjoint operator almost surely in L2 of R. The essential spectrum of that operator is the entire real line. But what is more interesting is that almost surely that spectrum is purely singular continuous if the field strength is larger than the variance over 2. And if the field strength is smaller than the variance over 2, then it's only pure point spectrum. In particular, it's dense pure point spectrum on the full line. This sort of refines results proved by Delion, Simon, and Souillard in '85, who studied the same model, possibly slightly different assumptions on the randomness than we have. But what they proved is that you have this kind of spectral transition from pure point to singular continuous spectrum when f over lambda squared goes from being small to being large. They did not have a precise transition, or they didn't even know that there was a precise transition. They only knew that sort of for non-explicitly small enough f over lambda squared, you have pure point, and similarly, if it was large enough, you had singular continuous spectrum. A similar result was proved by Minami in '92, who studied a related model, but where you replace this random Dirac comb by a white noise potential times a coupling constant lambda. He studied only a half-line operator, but obtained the corresponding result that we have. He had a sharp transition from pure point to singular continuous spectrum. Our sort of proof, or the method we use to prove this, is closely related to results proved by Kiselev, Larson, and Simon in '97, who were looking at a similar discrete model, where you had the discrete Laplacian plus random variables modulated by some decay, power-like decay, depending on the site. And they proved similar results here in the case when this decay is like 1 over the square root. That's a critical case. There they had a transition in energy from pure point spectrum to singular continuous spectrum. If the decay was faster, so if alpha was larger than 1/2, then you only have the AC spectrum, while if the decay is slower, you only have pure point spectrum. So this alpha being 1/2 is really critical, and you see the transition between singular continuous to pure point instead of just one of the two. Okay, so how do we prove these things? Well, the first step is something that is very standard in sort of this field, and it's to reduce everything to studying ODEs. And that is done by, in the deterministic model, a application of Gilbert-Pearson's subordinacy theory. And in the random case, you combine that with sort of the theory of rank 1 perturbations, and in particular, a spectral averaging argument in the style of Kotani. And what we're left with is trying to understand the asymptotic behavior of solutions of the generalized eigenvalue equation. So here I will actually also give you a formal definition of what we mean by the operator, these Diracs. So the ODE that we're looking at is solutions of the Stark equation in between the lattice points. That's not very surprising. And at the lattice points, we assume that our functions are still continuous. So J here denotes the jump of a function U at a point X. So in particular, our eigenfunctions should not have jumps at the integers, but the derivatives of them should jump proportionally to the value of the function. And now I will write G in here for the coupling constants, which in the random case are random variables depending on the site, and in the deterministic case are just all equal to lambda. So just for unifying of notation. So while it's sort of unfeasible to think that we could solve all of these equations for all energies simultaneously to any high precision, we don't really need to, because we only need fairly rough information about the behavior of these solutions. Specifically, what we need to understand is the existence or non-existence of subordinate solutions towards plus and minus infinity. And if there exist subordinate solutions, are they square integrable or not? And a subordinate solution is in the following sense a solution that is much smaller than all other solutions. In that if we have a non-trivial solution psi, it's subordinate to plus infinity. If for any linearly independent solution eta, the truncated L2 norm of psi grows much slower than that of eta towards infinity, and similarly towards minus infinity. Now, what Gilbert-Pearson subordinacy theory tells us is that if there exists a direction, so consider a fixed energy E, if there exists a direction either towards plus or minus infinity where there does not exist a subordinate solution, then you're sort of in the setting of absolutely continuous spectrum. If there exists a solution which is subordinate in both directions, then you're in the setting of singular spectrum. And whether it's singular continuous or pure point is determined on whether this subordinate solution is actually L2 or not. If it's L2, we have an eigenfunction, and then we have pure point. That's sort of standard. The power of the Gilbert-Pearson subordinacy theory is really in giving a fairly precise characterization of the singular continuous spectrum, which is usually sort of difficult to get your hands on. Singular continuous measures are not as nice as one might hope. Okay, so I'm not going to say anything more about these sort of black box results that we use, but jump directly to sort of the ODE results that correspond to the spectral theory that I stated before. So the first result is very boring, and you can essentially forget it after I've told you what it is. It states that everything is nice towards minus infinity. And this is the reason why I chose F to be positive. So towards minus infinity, we always have subordinate solutions, and they are always L2 integrable. So nothing interesting happens towards minus infinity. I even think these solutions are probably exponentially decaying, and everything behaves very nice towards minus infinity. So everything interesting happens at plus infinity. So for the deterministic model, we, in the setting of rational multiple of pi squared for the field strength, and away from this possible set of eigenvalues that we had before, what we want to show is that there exist no subordinate solutions towards plus infinity. All solutions behave the same way in the sense of this truncated L2 norm. So that doesn't look very interesting, although the spectral theory result might be more interesting than the random model. So in the random case, things get a bit more complicated, maybe more interesting as well. So here we fix field strength and energy and let the coupling constants be random variables as in the theorem. Then we have two statements. The first off is that if you fix a boundary condition at 0, so a deterministic Robin boundary condition, and look at a non-trivial solution of the equation towards plus infinity, then almost surely the solution you're looking at will satisfy that if you integrate the modulus squared on a unit interval from m to m plus 1, then that quantity is essentially m to the minus 1/2 plus lambda squared over 4f plus some small remainder, asymptotically. So typical solutions all behave this way. Now, if you sort of turn this around a bit, you can actually extract it from the proof of the first thing, that if you first pick your random sample and then pick a particular boundary condition at 0, depending on the random sample now, you can pick a boundary condition such that the corresponding solution satisfies different asymptotics. Namely, the same quantity instead behaves like m to the minus 1/2 minus lambda squared over 4f plus small remainder. So the second statement here is we have a subordinate solution because it's much smaller asymptotically than the typical solution. And we can also distinguish L2 integrability or not, depending on how large lambda squared over 4f is. And you see this cut off at 1/2. Yeah, that's f over lambda squared, that should be 1/2, which is the threshold that we were looking at between pure point and singular continuous spectrum. It might also be worth mentioning that we have corresponding asymptotics if we look at the derivatives of the eigenfunctions, but then the minus 1/2 in both cases is changed to a plus 1/2. So nothing drastic happens there. And also you sort of see in this theorem that the transition that we see in the spectral theory from being pure point to singular continuous spectrum, while that sounds like a very drastic transition, if you look at the solutions of the ODEs, it's barely noticeable. You have power-like decay all the time, and you just go to slightly slower power-like decay. So while I'm not a physicist, I suspect that physicists would not care about this transition very much. If we had instead the transition from sort of exponentially localized states to power localized, that would be a more substantial change to sort of dynamical properties of the system. So one should still think of this as some sort of continuous transition, even if it happens at a precise value. Okay, so how do we sort of approach proving these results? Well, the first step is, again, something that's fairly classical, although somewhat of a twist on the classical version of it, is to write these equations in terms of so-called preferred coordinates, or generalized preferred coordinates here. And the way we'll do that is, at least in a way that was described in some generality by Kiselev, Remling, and Simon in a paper from 1909, is to do sort of preferred coordinates relative to a background Schrödinger operator. But in sort of the specific case of the Stark operator, or random perturbation of the Stark operator, this was done also by Minami in 1992. It's also present in Buslav's paper. So while Kiselev, Remling, and Simon sort of set this up in a general framework and really formulated this as a version of preferred coordinates, the ideas had sort of been around before. So how do we do this? Well, we fix a reference solution, which I'll call zeta. It has an explicit expression in terms of Airy functions. You don't need to look at that. It's just to say that we know everything about this solution, since we know everything about Airy functions. The important things that we need from this is that, well, it's a solution of the Stark equation at field strength F and energy E. And we've chosen this solution in such a way that zeta and its complex conjugate are linearly independent solutions. So the Wronskian is non-zero and constant since they solve the same equation. Now, that implies that theta and theta bar span the entire solution space of the Stark equation, which is sort of the key property that we will use on the next slide. But that we can sort of use any old pair of solutions for. The properties of theta, or the specific choice of theta that we will use, is that it is in some sense a distinguished solution, in the same sense that the pure exponentials are distinguished solutions of the Laplace equation. And the quantity that will enter sort of into our analysis is the phase of theta, which we denote by gamma, so the complex phase. We can represent theta as e to the I gamma divided by square root of gamma prime, and gamma has an asymptotic expansion to any order in terms of powers of the square root of x, and this asymptotic expansion can be differentiated term by term. The only thing that you need to sort of keep in mind here, or I will remind you of it whenever you need to remember it, is that gamma behaves like x to the 3/2, and gamma prime is essentially a square root of x. Okay, so how does this help us with our ODE? Well, since theta and theta bar span the solution space, we can, in between any two lattice points, write a solution of our eigenvalue equation as a linear combination of theta and theta bar. If we assume that we work with just real valued solutions of the eigenvalue equation, we moreover know that sort of the coefficients in this linear combination have to be complex conjugates of each other. So we can write it as alpha times theta plus alpha bar times theta bar. So we get this sequence of complex numbers, one for each interval, and we can study our solutions in terms of these coefficients. So if you just plug this into the equation, you get a recursion equation for the alphas, which is the following. If we write un for the sort of effective coupling constant that we'll have here, which is minus gn divided by gamma prime n. Here I remind you that gamma prime is essentially a square root of n. So we have decaying coupling constants at a square root rate. Then the coefficients alpha and alpha bar at interval n plus 1 are those at the previous interval times a matrix an. And the matrix is unity times this effective coupling constant times an explicit matrix, which depends on this phase gamma. And it's not difficult to prove that if you integrate psi squared over this unit interval, it's essentially the absolute value squared of alpha divided by square root n. So if we understand the asymptotic behavior of the modulus of these alphas, we understand everything we need to about our generalized eigenfunctions. Now, these equations resemble very much the corresponding equations which appear in the setting of discrete Schrödinger operators, Jacobi matrices, but most closely they resemble those appearing in the spectral theory associated orthogonal polynomials on the unit circle. And sort of the reason that they resemble those the most is because we've formulated our choice of shape of the reference solution, that is theta and theta bar, imply that our transform matrices are in the group SU11, which is the case in the OPIC theory as well. If you look at sort of discrete Schrödinger operators, they are usually in some other symmetry group, but similar matrix group. And that's essentially just a conjugation by a symmetry here, to put it in that setting. However, there's one key difference between the equations that we have here and those appearing in the classical cases, namely that the phase that we have in these matrices is not linear. Typically, it's just a linear function of n. Here we have this nonlinear n to the 3/2 behavior, which causes some headaches, but also makes life a bit interesting. And to couple back to this square root decay that I mentioned, I said that in this Kiselev-Lust-Simon paper where they studied discrete Schrödinger operators on the one-dimensional lattice, this square root decay of coupling constants was critical. That you had, if you had faster decay, you had purely AC spectrum. If you had slower decay, you had only pure point. This square root decay that we get here is one of the reasons that we get this sharp transition between singular continuous and pure point. If we had sort of had a potential which grew faster, then we would probably have fallen into the pure point spectrum directly.
Can I ask a question?
Sure.
Yeah, so at the top of the slide, you've got the expression for psi as a linear combination of zeta and zeta conjugate. And anyone kind of looking at that and thinking, oh, roughly how big should the L2 integral of psi from n-1 to n be, wouldn't expect to pick up that extra factor of 1 over square root n that you've got in the integral.
Well, zeta decays like x to the 1/4.
Ah, okay.
I should have mentioned that.
Thank you.
It follows from this expression here. There's a square root of gamma prime here, but the Airy functions decay like x to 1/4. So it follows from the decay of the zetas. Okay. Yes. Any more questions on this? If not, then let's carry on. Good question. Okay. So these equations look sort of standard or look similar to the standard ones. So we do the same trick as you do in the standard theory. You pass from this complex formulation to a formulation in just terms of the real numbers. And the way you do that is you represent your alphas in polar coordinates. So we have some modulus r, which is a positive function. We divide by 2i to make some of the expressions nicer. And we have a phase eta. So we're going to write these equations that we had for alpha in terms of r and eta. For simplicity of notation, I also introduced theta here as this overall phase gamma plus eta, this prefer angle phase. So if you plug this into the equations that we had on the previous slide, you get two equations, one for r and one for eta. There are a couple of important features here. If we look at the second equation first, we see that it's completely independent of r. It just depends on eta and gamma. However, the cotangents make this structure sort of scary. But since un is actually small, you can Taylor expand this and get an approximate equation, which looks much nicer. I'll do that on the next slide. Secondly, the first equation is very easy to solve for r if we knew eta. Because if we knew eta, then we know theta, and then we can just take logarithms and sum and solve for r. So in these coordinates, the two equations decouple, which is sort of the power of these prefer coordinates that have been around since, well, I guess prefer. I don't know when he was around. Okay, so if we look at the R equation, which is the one that's most important to us, we're interested in the asymptotic behavior of the modulus squared of the alphas, which is r squared. We can rewrite it a bit. We divide by r and take logarithms and do a Taylor expansion of the log of this here. Now, using that the UNs, these effective coupling constants, are small, almost surely, we can justify this Taylor expansion. And we get sort of three terms that are important. First, we get one term, which is linear in U and comes with an oscillating phase sine of 2 theta. Then we get a couple of U squared terms, one which has no oscillations, and one which I've written with 2 oscillating terms. And then we have error terms above that, but this error term is summable in n. So it won't actually affect what we do here. So in this form, we can fairly easily iterate this equation and actually see what r is, or at least the logarithm of r. Namely, we sum this equation from n going from 1 to capital N, and we sort of get the asymptotic behavior of r as a sum of these UNs with oscillations. And you can do the same for the eta equation. It's a similar Taylor expansion of the cotangent this time. But all the terms sort of look similar. You have a couple of terms that are linear in U with or without oscillations. Then you have U squared terms with or without oscillations. So essentially, we need to understand these sums. First off, the terms where we don't have these trigonometric oscillations are fairly easy to understand. In the deterministic model, they're just 1 over gamma prime or 1 over gamma prime squared times lambda or lambda squared. And using the asymptotic behavior of gamma prime that we know to arbitrary order, we can compute the asymptotic behavior of these sums. Now, the ones with oscillations are slightly more tricky, or quite a lot trickier. And really what we have to do, and which is where the substantial work that we do goes in, is to understand exponential sums of the following form. Namely, we have, these are our effective coupling coefficients to some power, either 1 or 2. And we have an exponential which oscillates depending on this theta, which we don't know as well. And mu here is either 2 or 4. And well, Gn depends on which model we're looking at. So everything has essentially reduced to understanding exponential sums, which is not as easy as one might hope, but it turns out that we can actually do something here. And a key to that is that, at least heuristically, this is not really true, but almost true, theta can be viewed as a small perturbation of this known phase gamma. So I've got roughly 10 minutes left, so that's good. What I want to do now is to give you a quick overview of what we do in the random case. This is sort of a warm-up to the proof that that I'll skip here, but give some of the ideas of in the deterministic case and what we're able to say in the deterministic case. So first off, the random setting. So just to remind you, now the GNs are bounded, independent, identically distributed random variables with mean 0 and variance lambda squared. And just trust me on this, if you sort of translate the ODE results that I stated into these prefer variables, what we need to prove is that this logarithm grows like lambda squared over 8f times log n plus smaller order terms. And that's for the first ODE result, the one for typical solutions. The one for subordinate solutions can be extracted from this statement and its proof. So I'm not going to talk about that. That's essentially just abstract SU11 theory. Okay, so if we look at the terms that we had in the equation on the previous slide, I'm just going to look at the ones in the R equation, which is what we're interested in. We had one guy that was UN squared. We had one guy that was UN squared times oscillations. And finally, we had UN times oscillations. So we need to figure out how these sums behave asymptotically. And this follows precisely what Kiselev, Larson, and Simon did in '97. They had essentially the same sums. Instead of having gamma prime, they had the square root of n explicitly. Instead of having the nonlinear phase, they had a linear phase. But that's actually not going to appear much at all in our arguments. We're going to try to capture cancellations in these sums by using the mean zero property of these random variables, and that they have fixed variance as well. Okay, so if we look at the first sum first, we can rewrite it a bit. We sort of extract the mean value of the gn squares. We get something that's deterministic that we can calculate explicitly using the asymptotic expansion of gamma prime. That gives you this term. It's lambda squared over f times log n. Remember that the gamma prime is essentially a square root, so gamma prime squared is 1 over n, so this is a logarithmic divergence. The precise constant is just doing a more precise asymptotics of gamma prime. This term will precisely give us that term. There's a prefactor of 1/8 here that I've skipped. So the second term, well, now since we've subtracted the mean value of gn squared, this has mean value 0, and we can estimate the variance of these random variables, this full guy here, by 1 over n squared. Now these random variables are independent. The variance is summable. So Kolmogorov's 3 series test tells us that almost surely this sum converges. That gives us O of 1, almost surely. Now, we essentially do the same trick with the other sums as well. Things get slightly more complicated, but not much. The idea is the same. The second one, we split out the expectation of the GNs again. Now we still have these oscillations, which I remind you are random because theta depends on eta. But with these oscillations and using this at least heuristic argument that theta is essentially gamma, which behaves like x to the 3/2, you have a lot of oscillations here. Already without the oscillations, we only had a logarithmic divergence. So it suffices to use some fairly rough van de Corbet type estimates to show that this actually converges when we take into account these oscillations. Almost surely, I guess, here again. The second term, we can almost treat identically as we did the previous sum. There's one complication. The random variables here are now coupled. They are not independent because theta depends on the previous random variables gn. But the dependent structure is fairly nice. It's sort of a martingale type structure. And that is precisely what Kiselev, Larson, and Simon showed in their paper, that you can still sort of do a Kolmogorov 3 series test thing here and conclude that they almost surely converge. So the entire thing here is O of 1, which is good. And finally, the last guy, well, here we have mean 0 from the start. We have variance, which is essentially 1 over n this time. So it's not summable. But the Kiselev-Last-Simon idea is, instead of giving you an almost sure summability, it gives you an almost sure bound on how quickly this sum diverges. And it gives you that it's not much larger than the square root of the logarithm. So in particular, it doesn't contribute to this asymptotic expansion, and we're done. All the contributions came from this guy. Okay. So, right, as I said before, you can sort of repeat this argument and get the information that we wanted about decaying solutions by studying 2 linearly independent typical solutions and doing SU11 magic. Now, in the last 5 or so minutes, I want to talk about the deterministic model, which is much more complicated. But the idea is very much the same. We need to understand the corresponding exponential sums. But we can no longer use this big machinery of martingale estimates and probabilistic cancellations. But it should be noted that it's only the last sum that is problematic in the deterministic case. In the first 2 sums, everything works the same way. Well, these two guys are just zero in the deterministic case. This guy we can still compute, and the van der Corput estimates still work. They work easier without the randomness. You can prove that the corresponding sum converges, so it won't contribute. Actually, I haven't said what kind of asymptotics we want to prove, but trust me, it doesn't contribute. The only change is what happens with the last sum. And I want to emphasize, which is maybe not so surprising, because the spectral theoretic conclusions are very different in the deterministic model. The behavior of this sum is very different. In the rational case, which is where we understand it fully, the asymptotic behavior of the corresponding sum precisely cancels this logarithm. There's sort of just magical reasons that they precisely cancel out, and you get the AC spectrum instead. What we suspect in the irrational case, or at least sufficiently irrational, is that we should be closer to the random case, and that this magic precise cancellation should be weakened, and maybe we then go into either singular continuous or pure point, depending on to which order we actually have more cancellations due to the more random structure of this space when f is not rational. Okay, so what do we need to do in the deterministic model? We need to understand these exponential sums. The problem is that we can't yet. Now, I've cheated a bit here. We should really understand them with theta instead of gamma, but heuristically, it's essentially the same. And we can't, that might just be me and Rupert not being technically efficient enough, but they are certainly difficult to understand on this full scale. What turns out to be the case is that we can understand partial sums of these guys on scales that are much larger than sort of the lattice scale. And that will allow us to coarse grain our equation and prove sort of a behavior of the eigenfunctions on a larger scale than scale 1, which allows us to understand things at least to a more precise level and hopefully simplify the understanding even in the irrational case. So we want to sort of find a scale where we understand these sums. And while the scale is sort of naturally set by the phase, in these sums, we have strong cancellations unless gamma prime is close to an integer multiple of pi. If gamma prime is close to an integer multiple of pi, then this exponential essentially resonates with the lattice. And we don't have any cancellations, or at least not as strong cancellations. So we define a scale by sort of looking at the points where it's close to a multiple of pi. We find points xl given by pi squared over f L squared, which is precisely where gamma prime is a multiple, or it's pi times L. So a natural scale is essentially given by L squared, where L ranges through the integers. And by a somewhat delicate combination of Poisson's summation formula and a method of stationary phase computation, you can compute the sums that we are interested in when n ranges from L minus 1/2 squared to L plus 1/2 squared. So essentially we look at a sort of symmetric region around one of these resonant points x's, and sort of a partition of all of R into such regions. Now, what that leads to on the ODE side is the following sort of long theorem, which I don't expect you to read in detail. I just want to explain sort of the content of it for you a bit. So if we go essentially to the last conclusion here, it says that if we have, psi is again a solution of our eigenvalue equation, and it says that it can be represented again as a linear combination of zeta and zeta bar. This is our reference solution. But now the coefficients in this representation, which I now write as r tilde and eta tilde, are constant on this much larger scale given by this interval IL from L minus 1/2 squared to L plus 1/2 squared. So this is a scale that grows as L goes to infinity. And well, you have essentially the same representation, but we have an explicit phase shift. So this says essentially that the R and eta that we were looking at before are essentially constant up to an explicit change of eta on this much larger scale. Does that make sense? And well, it hadn't been interesting if we couldn't say anything about the R tilde and eta tilde. The interesting thing is that they solve essentially the same kind of equations that we had from the start. You again have square root decay in the main terms with some oscillations, and then lower order terms above that. Now, something has changed in these equations, namely the effective phase that we get. So theta tilde is something explicit plus eta tilde as before. But this explicit phase, which was previously our gamma, is now a capital gamma tilde, which instead of being x to the 3/2 is cubic in L to leading order. That's essentially the only change that has happened here. But this cubic behavior will allow us to utilize the rationality assumption on F. So while I know I'm officially 1 or 2 minutes over time, I have one more slide which explains why this rationality assumption comes in. So if it's all right with you all, I will give you that as well. So what is special with F, a rational multiple of pi squared? Well, from the equations on the previous slide, we need to understand sums of this form, perhaps with stronger decay, perhaps with a 4 here instead of 2, but similar exponential sums as we had before. And we want to coarse grain this equation again. This time we coarse grain sort of on a scale 1 relative to L by looking how R tilde and eta tilde change when L goes from Q times K to Q times K plus 1, where Q is this integer in the representation of F. Now, by a bunch of partial summations, you can actually prove that this sum is essentially the same as if we just pull out eta tilde at Qk and pull out the amplitude here as well. And then what we're left with is the sum of differences of this gamma tilde here. I pulled out this overall phase gamma tilde Qk. And this is where the explicit form of gamma tilde together with the rationality assumption come in to simplify life for us a lot. Namely, if you write out these two expressions, you get for gamma tilde Qk, this was cubic to leading order. You can expand the cubic. And what you get is something that's in an integer multiple of pi. Since we have a 2 here, we can ignore that, doesn't affect the phase. And then we get an effective linear phase in K. And linear phases we actually understand. So that's good for us. So what remains is to understand this sum here. But using the same sort of idea, we expand the cubics. You get something that's an integer multiple of pi. Again, we can ignore it. What remains is still cubic, but it's independent of K. So it's independent of the new sort of effective summation variable that we want to sum in later on. Just depends on this J, but that we just sum up to Q minus 1. So this guy here is independent of K. It's just an overall phase factor, which doesn't affect the effective recursion equations that we get after this second coarse graining. Now with this new effective problem, we have a linear phase, we have square root decay, we can actually understand what happens. And that leads to R tilde actually having a finite limit, leads to R having a finite limit, which leads to non-existence of subordinate solutions, leads to AC. That's the proof in a very small box for a much longer proof in principle. And since I'm already over time. I'm going to skip sort of my summary and conclusions, and thank you all very much for your attention.
Thank you very much, Simon. Some physical and some virtual clapping. So any questions for Simon? If not, I will start. In the stochastic case, so what happens if you say don't have IIDs? So do you really need IIDs or?
No. We need independence. I think we could pass to sort of asymptotically independent, but IID certainly not. I sort of stated it in the IID case here just because it's simpler. We need one of them to have absolutely continuous distribution. But apart from that, we need very little. Some moment bound, I think a fourth moment bound suffices. So yeah, the IID is much stronger than what we need, but it gets technical if we assume this.
So it's not an essential assumption.
No. Okay. And you essentially saw that in the proof of these oscillatory integral sum estimates.
Yes, you were using.
Kolmogorov test never uses the identical distribution. You need the moment bound. That's it, and independence.
Right. Thanks. Any more questions? Yeah.
So you mentioned that when gamma dashed is close to an integer multiple of pi, you get what you call the resonance with the lattice. Is there any sort of physical understanding of what that means?
Well, when Buzlaev explained his heuristic argument, why the spectrum should be as he predicts, he does not motivate these points XL in the same way that I do. And we actually follow very closely to a paper of Perelman here, who studied less singular potentials. But Buzlaev motivates it from these being turning points for the equation. Now, I don't fully understand this picture, but if you look at the Kronig-Penney model, so you put the field strength to 0, then you have the band gap structure of the spectrum. And if you move sort of the start potential to the other side of our equation, so you have Kronig-Penney equal to energy plus Fx times eigenvalue. Buzlaev motivates the significance of these points XL, points close by at least, by saying that those are the points where the combination energy minus or plus Fx is in the gaps of the Kronig-Penney model. So essentially he looks at Kronig-Penney equal to sort of a perturbed eigenvalue equation where, well, there's very strong perturbation by the linear potential. And he says that, well, this quantity being in the gaps should have significant effects on how the behavior of the eigenfunctions changes. And that happens in regions essentially given by asymptotically given by these points. That's precisely where this quantity falls in the gaps of the Kronig-Penney model.
Thanks.
Does that make sense?
Yeah, that's very useful. Thank you.
More questions? That doesn't look like to be the case. So let's give a second round of applause for our speaker. And let's thank him for the very nice talk.
Thank you again for the invitation.